Welcome back. In today's lecture, we'll discuss how to use additional physical information for reducing the number of independent pi numbers. Let's consider the example of pressure loss in a flow of fluid within a pipe. Delta P, the pressure difference at the two ends, depends upon the density of the fluid, the viscosity of the fluid, the average velocity of the fluid through the pipe, the diameter d of the pipe, the length L of the pipe, and epsilon, a roughness parameter, typically the average height of roughness on the surface of the pipe, inside surface of the pipe. We see here the total number of parameters involved is 7, and if we work in MLT system, the number of independent dimensions is 3. And with this, if we carry out a dimensional analysis like we have carried out in last few classes, the non-dimensional pressure difference parameter delta P divided by 1/2 rho V average squared is a function of rho average D divided by mu, which you recognize as Reynolds number, L by D, length or diameter of the pipe, and epsilon by D, which is called the roughness parameter, relative roughness, epsilon by D. This is not a very expressive expression because of the 3 independent pi groups involved on the right hand side. We like to reduce them. Can we use some additional information to reduce the number of parameters on the right hand side? Yes, we can. Since the condition in a fully developed flow do not change along the length of the pipe, the shear stresses at the valve would be constant along the pipe, and therefore we expect the pressure drop per unit length to be constant. This is an additional physical insight that we bring in to solve the problem. If the length of the pipe is very large compared to diameter, then we can assume that the things don't change in the z direction, that is along the axis of the pipe, and if that does not happen, then the pressure drop would be constant per unit length. In other words, delta P over 1/2 rho V average squared should vary linearly with L. If it varies linearly with L, then the dependence of the function should be like delta P divided by 1/2 rho V average square should be L by D times function f of rho V average D divided by mu, the Reynolds number, and epsilon by D, the relative roughness parameter. This is the famous formulation that you must studied in your fluid mechanics course. Now you notice that the function f is a function of 2 parameter groups, the Reynolds number and the relative roughness parameter. And so it is possible to plot a curve between f, which is termed as the friction factor, and the Reynolds number Re, with epsilon by D used as a parameter to get different curves. The resulting curve is known as Moody chart. And in this Moody chart, we have different lines, each line representing a relative roughness parameter. And then there is Reynolds number along this axis and the friction factor F along this axis. For any pipe, we can calculate the Reynolds number. Let the Reynolds number be, for example, 10⁻⁶. 1 million. Then we enter along this axis, and suppose the relative roughness of the pipe is 0.02. Then we get to this point, and then we go to this axis and read the friction factor. Once we have determined the friction factor, I can determine the pressure drop. Delta P divided by 1/2 rho V naught square is F times L by D. This F we obtained from here, and L by D we know. So using the physical fact that the pressure drop should be proportional to length of the pipe, we have been able to reduce the number of parameters on the right of the equation, that is the number of independent parameter groups, from 3 to 2. And the two groups, we are able to plot a graph, and from this graph we can determine the value of F. This is substantial improvement on the result. So we read the value of F as 0.023 from here. We have used the argument of full development. The full development is a kind of a symmetry argument. The choice of the origin of the axial coordinate system in an infinitely long channel is arbitrary, i.e., the change of the origin does not affect either the governing equations for velocity field or the boundary conditions. In this pipe, if I choose the origin of Z, the coordinate along the axis of the pipe, as at this point or this point, and if this pipe is truly infinite in length, then it doesn't matter where we choose the origin. The equations as well as boundary conditions do not change. Do a thought experiment. Suppose you're looking at this pipe and you blink your eyes, and when the eyes are closed, somebody moves the pipe through a distance. Then would you know when you reopen your eyes that the pipe has moved? No. The picture should appear to be exactly the same as before. This means that the conditions are independent of the coordinate Z. Therefore, the solution of the velocity field should not be a function of the length variable in the axial direction. Thus, the velocity should not be a function of the axial coordinate. This is termed as full development. For velocity profile, this is very simple. The velocity profile is independent of Z. But we have a little complication in the temperature profile. Suppose again we have two parallel plates now, and these two parallel plates are at two different temperatures with the fluid flowing in between. Let the lower plate be maintained at temperature T2 and the upper plate at a temperature T1. If the plates are of infinite length in the Z direction, then as before we can argue that the picture should not change as the origin changes. And because of this, the temperature profile should be independent of Z. dt by dz should be 0. As shown, the temperature profile at this location and this location are identical. But now, let's consider the flow through a pipe. Now you do not have two walls, only one continuous wall. Let the temperature of this wall be Tw. And let us consider the case when there is a constant wall flux, the heat transfer across the walls of the tube. is independent of z, the axial coordinate. And if this happens, the heat flux Q can be written as H times Tb minus Tw, where Tb is the bulk temperature of the fluid. The bulk temperature, as you recall, is something like average temperature of the fluid. If you take the fluid at a given location and you let it run into a mixing cup and mix it up, then the resulting temperature is called the bulk temperature. So the heat flux is H times the bulk temperature minus the temperature at wall. Now the temperature cannot be constant since the heat flux is moving continuously into the wall. Then the temperature of the fluid, the bulk temperature of the fluid, must be increasing linearly. Heat flux is constant, the rate of increase of the bulk temperature must be constant. And from this equation we get, if Tb is increasing at a constant rate, Tb minus Tw should also be constant, and because of this then Tw must also be increasing at a constant rate. This difference of temperature, Twall minus Tb, should be constant with Z. So when we look at this picture, it is not the temperature that is invariant with the Z, but the temperature difference Tw minus Tb that is invariant with the Z direction. So any heat transfer from the wall will make the fluid temperature increase or decrease steadily in such cases. We could define a temperature difference variable theta is equal to T minus T reference. The temperature difference variable with T reference is equal to T wall should be invariant with Z. Now recall again that when you look at heat transfer equations, these are not temperature that occur there, it is a temperature difference that occurs there. So we could introduce a temperature difference variable theta. That is, we can measure T relative to any reference temperature. Here we have chosen reference temperature to be the wall temperature, the local wall temperature. And if we do that, the temperature profiles at two locations would look like this. Tw here is this, from here to here. At a little later location, Tw is larger. The bulk temperature at the first location is somewhere here. In the second location, the bulk temperature is somewhere here. The difference between Tw and Tb is the same at two locations. And if the flow is fully developed, the temperature profile is fully developed, then this blue profile, which is T minus Tw or Tw minus T, should be invariant. So the full development in temperature profile means that it is not temperature that is invariant with Z, but it is the temperature difference theta, which can be defined as Tw minus Tb or Tb minus Tw, which is invariant with the Z direction. Thus this is an invariant temperature difference profile. Let's next do the other case of heat transfer in a pipe, which is usually done is when the wall temperature of the pipe is assumed to be constant. If there is a constant wall temperature, then the temperature profiles down the pipe look like this. TW is constant, but the heat is being transferred into the pipe, that is, to the fluid within the pipe continuously, so that the bulk temperature of the fluid is increasing. The temperature difference TW minus TB is decreasing. What does that mean in full development? Let's look at temperature profile at two different locations. TW is constant. The bulk temperature is increasing. So, the temperature profile, even this blue profile, which is the temperature difference profile, is changing in shape. But there must be something that is constant, something that is invariant with Z. And what is that? We discover that it is the normalized temperature difference, theta star, which is the temperature difference, theta T minus TW divided by TB minus TW. That has a constant shape. If I plot this at this location, or at this location, or at this location, I will get the same picture. So, it is this which is invariant. An interesting argument. I thought I'll cover it here because it fascinates me. So, let's summarize the argument that we have enunciated in the last couple of slides. The full development in temperature profile in pipe flow or in flow between two parallel plates can be expressed by saying that normalized temperature difference theta star, which is defined as T minus reference temperature divided by characteristic temperature difference, is independent of Z. Del theta star by del Z is 0. For two parallel plates with two different temperatures T1 and T2, we can choose T reference to be T1 or T2, and the characteristic temperature difference is T1 minus T2. And if we do this, we'll get invariant normalized temperature difference profile. For flow with constant heat flux in a pipe, the bulk temperature is changing. Here we use T reference as the wall temperature TW and the characteristic temperature difference as the local bulk temperature minus the wall temperature. So, TW is changing with Z. Delta Tc is changing with Z. But T minus T reference divided by delta Tc is invariant with Z. The final case we did was a constant wall temperature in a pipe. Here again, T reference is T wall and the characteristic temperature difference is the local bulk temperature minus the local wall temperature. Tb as well as Tw are functions of Z, and then theta star defined here is invariant in this case as well. Let's do another example where we will use physical information to simplify the expressions that we obtain through dimensional analysis. Let us consider the terminal velocity of a falling sphere in a viscous liquid. Clearly, This terminal velocity v will depend upon the density of the sphere rho sub s, the diameter d of the sphere, the density of the liquid rho f, and the viscosity mu, and of course the acceleration due to gravity g, because gravity is what is causing the ball to fall. If we work in MLT system, we write the dimensions of all the parameters involved. There are 5 independent parameters and 1 dependent parameter. Dependent parameter V written in red. The dimensions of all of them have been written down. Then we choose the basic group as the density of the solid sphere, the diameter of the sphere, and viscosity. These 3 we choose as the basic group. Now there are 3 remaining parameters, 1 dependent and 2 independent. So this will mean that if we work with this, we'll get 3 pi groups. To obtain the pi groups, we express the dimension of these remaining parameters in terms of rho s, d, and mu, using the method that we discussed in the last few lectures. And if we do this, the dependent parameter results in a dependent group V rho s d divided by mu, and 2 independent groups of parameter, 2 independent pi's. The ratio of the density is rho f by rho s, and g rho s square d cubed divided by mu square. This is not a very expressive relationship. So can we bring in some physical information? Yes, the only meaningful function of rho f by rho s for this problem is 1 minus rho f by rho s. That is the difference in densities normalized by rho s. Actually, we should be concerned only with the difference in densities. That should derive this. So, we can take this first parameter out, and the function of this will have to be of this form. So this has simplified the problem considerably. So now we have only 1 parametric group whose dependence is unknown. We can do experiments to determine this. But the relation of rho f divided by rho s should be of this form. This is from the physics that we bring in. The same result. We can further assert that the acceleration g due to gravity should occur here only in the context of buoyancy force. Or in the combination g times rho s minus rho f. And if this is so, then the functional form should be like this. The normalized terminal velocity should be a function of this parameter, one parameter. And now we can determine this by conducting experiments of that form. Instead of taking 2 steps to arrive here, we could have started out with a formulation that velocity is a function of rho s, d, the diameter, mu, and the wet weight of the sphere. That is the net weight. That is the weight of the sphere minus the buoyancy, the force that moves the sphere downwards. And net weight is proportional to the density difference times g. So instead of using rho f and g separately, we could have used this in this combination. And if we had done that, we would have arrived at this equation directly. This again illustrates how physical information can be used to augment dimensional analysis. Let's consider a thermal problem where we will bring in additional information. Consider the total heat transfer rate from a long, thin wire of diameter d and length L. Long, thin wire means L is much larger than d. And it has very high conductivity. The wire is initially at temperature T0 and is immersed in a fluid with specific heat capacity Cp, the density rho, conductivity K, and the temperature Tf, and moving past the wire with the velocity v. So the rate of heat transfer from the wire, Q dot, is a function of the properties of the fluid, K, conductivity, rho density, Cp, the specific heat, the geometry parameters of the wire, the diameter and the length, the two temperatures, T0, the initial temperature of the wire, and Tf, the temperature of the fluid bath, and V, the velocity of the fluid relative to the wire. There are a total of 9 parameters. For physical problem where there is no or negligible conversion of mechanical energy into thermal energy, it is convenient to just introduce 2 additional dimensions besides M, L, and T. The dimensions are Q for heat energy and theta for temperature. That is for thermal energy or heat and temperature respectively. So that gives the number of dimensions involved R as 5. N is 9, R is 5. So we expect to have 4 groups of parameters, 4 pi's, 1 dependent and 3 independent. Dimensions of various quantities in Q, theta, M, L, T systems are these. If we had used MLT system, the dimensions would have been these, but we are not concerned with this here. In this system, this table represents dimensions of all the 9 quantities involved. Q dot, the rate of heat transfer, has a dimension of Q1 and T minus 1. We can deduce the dimensions of K and Cp, which have been deduced here and transferred here. So these are all the dimensions involved. It can be argued that the heat transfer should depend on temperature differences rather than temperatures, as we had done earlier in this lecture. So T naught and Tf should be together to define delta T as T naught minus Tf. Thus, number of independent parameters is reduced by 1. From T naught and Tf separately to a combination delta T. Similarly, the sole function of density should be to define mass that provides heat capacity, so that rho and Cp should occur as a product rho Cp, not independently. Rho should not occur anywhere else. There is no function of inertia that it serves. Cp also should not occur anywhere else except in the combination rho Cp. Thus, we can express Q dot as a function only of 6 independent parameters: K, rho Cp together, D, L, delta T and V. We can determine when we do this, the basic set will consist only of 4 quantities and not of 5, and so that number of pi's will be 7 minus 4, 3. So there is a reduction of 1 pi that we have been able to achieve by bringing in this physical information. Here we carry out the dimensional analysis. We construct the table of dimensions again. Since there are 4 basic quantities involved in the basic set, we choose rho Cp, K, D and delta T as the basic quantities, highlighted with the yellow tint here. There are 3 other quantities left, 1 dependent and 2 independent, Q dot, L and V. So it will result in 3 pi's. We express the dimensions of Q dot, L and V in terms of the basic set. And this is what we get. And from this, we get a dependent non-dimensional parameter Q dot divided by K D delta T. That is, we get Q dot divided by K D delta T as a function of V D rho Cp by K and L by D. Rayleigh in 1918 went further. He invoked that the heat transfer from the wire should be similar to that from a flat plate, where Q dot varies like under root velocity. He therefore postulated that wherever the velocity occurs, it should be to the power 1/2. So that he was able to write this, again based on additional physical information. I repeat here the expression from the last slide. And this is of the form Nusselt number is equal to C Re Reynolds number into Prandtl number raised to power 1/2. From this, we can get this. This combines with this to produce Nusselt number. And this is the standard correlation that is used in convection. Let's do another example of a free convection on a vertical plate. Shown here is a vertical plate, hot plate in a cold fluid. Plate heats up the fluid next to it. The heated fluid is now less dense, so it experiences a buoyancy force. The fluid starts moving up. And as it moves up, it is replaced by the colder fluid from below. The heat travels in that direction and its fluid is swept up in that direction, so that limits the region which is affected by heat. So this shows the extent of what is termed as a free convection boundary layer on a vertical plate. The heat transfer coefficient H in free convection from vertical plate depends upon the properties of fluid like density rho, viscosity mu, conductivity K, and the heat capacity Cp of the fluid. The length Z along the plate, Tw the wall temperature, and Tf the temperature of the ambient air. And it also depends on the buoyancy force, which depends upon beta, the coefficient of thermal expansion of the fluid, the fractional rate of change of density with the temperature, beta, and of course on G, the weight per unit mass, the acceleration due to gravity. So H can be written in this functional form. Depends upon the properties of the fluid. This again is the property of the fluid. The two temperatures, the length of the plate in the Z direction, and G, the acceleration due to gravity. There are 9 independent parameters. We'll repeat the expression here. It's a very large number of parameters. We should use whatever physical information that we have to reduce the number of parameters as much as possible. Note that heat transfer depends not on individual temperatures. We used that argument a couple of times earlier, but on the temperature difference, so that it is not Tw and Tf that matter, but delta T is equal to Tw minus Tf that should enter the list of parameters. So these two parameters would combine to give only one parameter, Tw minus Tf. This reduces the value of n by 1. Further, the fluid motion in the vertical direction depends upon the buoyancy force, which in turn depends upon the combination G beta rather than G and beta independently. Beta would result in a density difference, and that multiplied by G will give you the buoyancy force. So this means that these two combine to give Bg, and that further reduces n by 1. So that the original equation modifies into this equation. 7 independent parameters and 1 dependent parameter. Total n is equal to 8. And work in MLTQ theta system, we need R is equal to 5, which gives 3 non-dimensional pi's. The table in the next slide facilitates the organization of this information. The dependent parameter H is never selected in the basic group of parameters. So we have chosen the basic group at Z, rho, mu, K, and delta T. 5 of them independent and complete. Independent in the sense that you cannot express any one of them as a product of power of the rest within this group. And complete in the sense all dimensions that are relevant, the 5 dimensions here, are contained there herein. These are the 3 other parameters which remain: H, the dependent parameter, Cp, and G beta together. The dimensions of these are written in this line. You can verify. And now we want to write each of these other parameters as a product of Z raised to power A, rho raised to power B, mu raised to power C, K raised to power D, and delta T raised to power E. And when we do this, the dimension of these products should match the dimension of the parameter that we selected from the others group. So with H, the dependent parameter, we get a dependent pi, and it is 0 raised to power 1 and K raised to power minus 1. And from this, we get a parameter Hz by K as a dependent non-dimensional parameter. This is termed as Nusselt's number and abbreviated by Nu in heat transfer literature. From Cp, I get the dimension of Cp as a dimension of mu raised to power C, K raised to power D, and delta T raised to power E, with value of C as 1, value of D as minus 1, and delta T as 0. So that the non-dimensional parameter that we formulate is this. And this is recognized as Prandtl number, which is abbreviated as PR. And G beta involves Z, rho, mu, and delta T, and these are the exponents there, which results in this parameter. And this is recognized as what is termed as Grashof number, which is important in free convections alone. So the result can be expressed as Nusselt's number is a function of Prandtl number and Grashof number. Those of you who have completed a course in heat transfer know this empirical relation very well. It is possible to improve this result by resorting to what has been termed as directional analysis, where the length dimension L is broken up into 3 mutually perpendicular dimensions, Lx, Ly, and Lz. This we will do a little later. Let's go further and look at what else can we do. Asymptotic behavior of the function is something that we must consider. When there are only 2 parameters involved in a problem, then we get an expression like y is equal to function of x. A dependent parameter y as a function of a single independent parameter x, where x is either very small or very large compared to 1. Since we are talking of non-dimensional parameters and normalized So we expect them of order 1. But suppose these parameters are very small or very large compared to 1. In such cases, there are 3 possibilities. One is fx approaches a dimensionless constant value c. X and y both are dimensionless. So function fx approaches a dimensionless constant value c. The second possibility, this approaches a power law, c times x raised to power n, where n is non-zero. And third, of course, none of these. Now, first and second are about the same. The first is a special case of the second possibility with the value of n as 0. So first and second can be combined to say that fx approaches a power law cxn, where n could be 0 or non-zero. Of course, dimensional analysis alone does not reveal the asymptotic behavior. We'll have to draw on a physical knowledge. For this, consider the case of a cable which is hanging and under its own weight, it extends. So from the ceiling, we have this long cable, long thin cable. So the length of the cable L is much greater than its diameter. The extension of this cable delta would clearly be function of L, the length, rho prime, which is the mass per unit length of the cable. So the density time cross-sectional area, rho prime, mass per unit length. G, the acceleration due to gravity or weight per unit mass. And E, the elasticity of the cable material. Now we bring in the physical fact that since the cable extends under its own weight, the rho prime G may be considered to be together, not independent of each other. So that instead of 4 independent parameters, we have only 3 independent parameters. Now there is no need of work in MLT system. Force and length are the only 2 dimensions that are involved, and if we construct the dimensional table, that's what it looks like. 2 dimensions FL, delta is a dimension of length, length of course is a dimension of length, rho prime G is a dimension of force per unit length, and E is force per unit area. So we choose L and rho prime G as the basic set, and in terms of this basic set, we obtain the dimension of delta as L raised to power 1 and of E as L raised to power minus 1 and rho prime G raised to power 1. And this gives us delta by L is equal to a function of E divided by rho GL, or delta can be written CL times the function of rho G divided by EL. Now for most cables, the non-dimensional parameter rho prime G divided by EL has very small value. Rho prime would typically have a value in SI system as 10 to the power 3 or so. G has a value about 10. So numerator is about 10 to the power 4. The value of E, the elasticity, for most material it is of the order of 10 raised to the power 8 to 10 raised to the power 10. In L, the length of the cable would definitely be in meters. So this parameter rho prime g divided by EL has a value of at least 10 raised to, or at most 10 raised to the minus 4 or 10 raised to the minus 5. A very small value compared to 1. So the functional form should be like this. Y as a function of x, x becoming very small. So the functional form should be like x raised to the power n. Now, we could draw some arguments about the value of n. Here the n must be positive, because if n is not positive, then delta would not increase with the change mass. Rho prime. Heavier chain, rho delta should be increasing with rho prime, not decreasing. That means n must be positive. Physical information brought in and some opinion formed about the value of n. N must be positive. Further, because the longer cables should stretch more than the shorter ones, delta should increase as a positive power of L. So the value of n should be less than 1. Otherwise, L in the numerator and L raised to the power n in the denominator. If n is greater than 1, then delta would decrease with L. It's not possible. So n should be less than 1. Therefore, n must have a value between 0 and 1, both ends excluded. Neither 0 nor 1. In fact, there is reason to believe that the value of n is about 1/2. Let's do one more example. An interesting example. If we sit in a car with one window open, that at certain speed you hear a very low bass sound within the car. One of the car windows is open, not all 4 windows, only one window is open, and you hear a very low bass sound, low frequency sound. And this could be very irritating. The only way to stop the sound is either to close all windows or to open all windows. If only one window is open, then you hear this bob, 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 bob sound, which is very irritating. And why is this happening? It's happening because of an interesting phenomenon known as the resonance in a Helmholtz resonator. Helmholtz resonator is a volume with a neck. The volume serves as a spring and the mass in the neck oscillates. Given a volume and given the neck dimensions, there is a particular frequency at which this resonates. And so you hear that sound. Helmholtz has analyzed this, a volume V with a neck of cross-sectional area A in length L. It's like a mass on a spring. This air volume serves as a kind of a spring. This is a mass that oscillates. Helmholtz found the frequency for this mass. This is a very important innovation. It has been used in old churches to produce sound damping effects. It is also used in a muffler. If this is exhaust or an airstream, then if we can make a Helmholtz resonator with a frequency of the sound carried in here, then the energy from this stream, acoustic energy, would go into the resonator, and if you put some damping material with the resonator, then energy would be taken out. And so this could work as a muffler. But in a car with the window open, this is producing noise. So the frequency of this resonator is a function of V, the volume. In our case, it would be the volume of the cabin of the car, P, the air pressure, rho, the air density, A, the area of the open window, and L, the thickness of the neck that is formed by the open window. So if we write the dimensions of all these parameters in the M, L, and T system, this is the table that we get. We choose the basic set as V, the volume, the pressure, and the density of air. And these are the three groups that are formed from omega, A, and L. So that this is the functional equation that we get. Can we get further information from this? That functional relation repeated here. A resonator with the same shape yet of different sizes, that is having the same ratio A divided by volume raised to power 2/3 and length divided by volume raised to power 1/3, this and this, same values, different sizes, but same shape. So if these two parameters are same, then omega is a function of V raised to power 1/3 with a negative sign. Large volume of the car give you very low frequency. So a bass sound that you get. The common experience. However, we also know that the value of A divided by V raised to power 2/3 and L divided by V raised to power 1/3 are very small for a typical Helmholtz resonator, and definitely for the passenger compartment of a car. The volume of the car, the area of the window, and the thickness of the window opening. Thickness of the window opening area are much smaller than the volume of the car is to power 1/3 or 2/3. So these two parameters are tending to be very small. And so we can write omega in this form according to the discussion that we had previously. So we have learned here in today's lecture about how to simplify the results obtained from dimension analysis by supplementing with additional physical information. Thank you.